Have you ever stopped to wonder how a self-driving car tells the difference between the road and a pedestrian? I mean, not just knowing that they're there, but knowing exactly where the edges of the person end and the sidewalk begins? Well, today, we're going to dive into exactly that, how we teach computers to see our world in incredible pixel-level detail.
You know, when a computer looks at an image, it doesn't see a cat. It sees a grid of numbers, a matrix of pixel values. And that's the fundamental challenge, right? It's all right here. How do we get from that simple grid of numbers to a rich, complex understanding of a cat? It turns out teaching a computer to truly see isn't just a single flip of a switch. It's actually more like a journey, a series of levels, each one getting more complex and more detailed than the last. So let's walk through them.
Okay, so level 1, the most basic starting point, is what we call image classification. The task here is super simple. Just look at the whole image and tell me what's in it. It's all about the big picture, not the little details.
So you give it an image like this one, and a classification model just spits out a list of labels. It knows there's a cat, some grass, a tree, the sky, but it has absolutely no idea where any of those things are. It's a start for sure, but it's pretty limited, right? So let's climb up to the next level, object detection. Now, this is a huge step up, because now the computer doesn't just identify what objects are in the scene, it also figures out where they are.
And this picture shows it perfectly. Instead of just a list of words, we get these bounding boxes drawn around each individual thing it recognizes. So now it can count them, it can locate them, it can tell them apart. We're getting a lot closer to a real, genuine understanding of the scene. But what if a box just isn't good enough? I mean, what if we need to know the exact shape of everything, down to the last pixel? Well, to do that, we have to get to the ultimate goal of today's explainer, semantic segmentation.
Now here's where it gets really interesting. We're not even thinking about objects anymore. We're thinking about pixels. The goal here is to classify every single pixel in the entire image. The best way to think about it is like a digital coloring book. The AI's job is to color in all the pixels that are cow, all the pixels that are grass, and all the pixels that are sky, and to do it perfectly. So, how on earth do you even begin to do that? Well, the first idea people had was pretty intuitive, but as we're about to see, it was incredibly, painfully slow. It's kind of like trying to appreciate a giant painting by looking at it through a tiny little peephole. This first method is called the sliding window. And the logic makes sense, right? You just take a small chunk of the image, a patch, and you feed it into a regular image recognition network, what's called a CNN. That network looks at the patch, and then it makes a decision about the one single pixel right in the middle. And then you just slide that window over one pixel and do it all over again and again for the entire image.
Let's just watch this in action for a second. We start by grabbing a tiny little patch from the image, let's say right around the cow's eye, and we feed that little square of pixels into our neural network.
The network looks at all the textures and colors in that tiny patch and makes a call for that center pixel. And in this case, yep, it correctly decides that pixel belongs to the cow category. Okay, one pixel down, millions to go.
All right, next, we slide our little window over to a new spot. Now the patch is mostly grass, but it's got a little bit of the cow's nose in it. We take this new patch and feed it into the exact same network. And, you guessed it, the network looks at this new context and classifies the center pixel as grass. I'm sure you can already see the problem here. Can you imagine repeating this process for every single pixel on a high-res photo? It would take forever. It's just not practical.
This massive inefficiency was a huge roadblock for a long time. So to solve it, researchers needed a totally new way of thinking, a real breakthrough that involved, well, looking at the whole picture at once.
So here's the core of the problem, right here. With that sliding window, every time we nudge the patch over, the computer is recalculating a ton of information for pixels it's literally just seen. All those overlapping patches? It's a massive, massive waste of computing power. So the big conceptual leap was this. Why are we analyzing millions of tiny, overlapping patches one by one? Why not just build a network that's smart enough to process the entire image in one single go, to understand the context of the whole scene from the very start? And the answer to that question is the hero of our story today, the Fully Convolutional Network, or FCN. And this was a total game changer, not just because it's way, way faster, but because by taking in the whole image at once, it gets this holistic understanding. It can actually see how objects relate to each other. It's this special kind of network that can take a big image as its input and spit out a complete map of labels that's the exact same size.
Okay, but how does it actually do that? How can a network look at a huge detailed image and then output another huge detailed image with pixel-perfect labels? Let's get into the secret sauce.
It's really this beautiful, elegant two-step process. First, the network compresses the image, shrinking it way down. We call this downsampling. Now, in this step, it loses a lot of the fine-grained details, but what it gains is this powerful, high-level understanding of what's going on. It gets the gist of the image. Then, in step 2, it cleverly reverses the process. It upsamples that simple, coarse map back up to the original size, creating the final, detailed output.
And that just leads to the key question, right? Once you've squished all that information down, how do you blow it back up without it just looking like a blurry, blocky mess? How do you intelligently upsample?
Well, there are a few pretty simple ways to do it. On the left, you have what's called bed of nails, which is, well, it's basic. It just plops the pixel in the corner and fills the rest with zeros. A little better is nearest neighbor on the right. It just copies the pixel to fill the whole new space. It works, but as you can see, you end up with a really blocky, pixelated look. A much, much smarter solution is called bilinear interpolation. Instead of just copying pixels, it intelligently creates new ones. It looks at the values of its neighbors, so here, the 1, 2, 3, and 4, and it calculates a weighted average to fill in all the gaps between them. See that new pixel with a value 1.75? It's calculated based on how close it is to all 4 of those original points. And this creates that smooth, natural gradient, which is exactly how we get those clean, precise outlines in the final result. So there you have it, from a simple cat label all the way to coloring in every single pixel in an image. That is the journey of semantic segmentation. This technology is already at the heart of so many things, from self-driving cars navigating city streets to medical AI that can outline tumors in scans with superhuman precision. It is fundamentally changing how machines perceive our world. And it really just leaves us with one incredibly exciting question. What will AI learn to see next?